Hello and welcome to today's PIR live event webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. Please remember, if you're joining us live, you can ask questions anytime throughout the webinar. No need to wait until we're already in the Q&A section. Just click chat near the top left of your screen. Make sure you change the to field of your chat message so it includes attendees, and then let us know what it is that you're wondering, and we'll queue up that question for when we have time to answer it. Make sure you let us know whose question that is, or what class it's from, or what city, and we'll be sure to give you a shout out when we ask your question. So today's guest is Dr. Jennifer McKellar. She is an assistant professor in the Faculty of Energy Systems and Nuclear Science at the University of Ontario Institute for Technology, or UOIT. Thanks so much for joining us, Dr. McKellar. I will let you take it away.
Thank you very much, Stacey. So I'm very happy to be here. My research is on the technical and environmental assessment of energy systems. So I've done some work related to oil sands, some work related to electricity generation in Ontario, some work related to nuclear plants. And so I'm really looking at how each of those different energy technologies, how they fit into the broader system that goes around them, and then the impacts that they have on the environment and how much they cost, because cost is so important to how we use energy. So I thought I'd just introduce you today to sort of the systems approach to energy systems, and one of the major tools that we use to make those assessments. So I'm just going to share my slides here. Okay, so hopefully that worked. Okay. So I guess to start off, I'm sort of assuming everyone is familiar with greenhouse gases. So greenhouse gases are the carbon dioxide, the methane, the nitrous oxide that we get from a lot of different places, but one of the biggest sources is burning fossil fuels. So things like coal, natural gas, oil, gasoline in our cars, they produce these greenhouse gases. And our problem is that the greenhouse gases are accumulating in our atmosphere, and they're capturing the heat that's being released from our planet and keeping it in the atmosphere and changing our climate. So one of our biggest goals, one of our biggest challenges is to minimize our releases of greenhouse gases while not losing any of the services that we really want, right? We still want to be able to get from home to school, and we still want to be able to watch TV and charge our cell phones, but we don't want to be releasing greenhouse gases as we do it. So that's one of the things that many people have been working on for a long time. So a systems level approach to that problem tries to take us beyond sort of the immediate energy technologies that we see in front of us and look at the big picture that goes around them. So I've got my fancy car here with exhaust emissions. And so if this car is just burning conventional gasoline, it's emitting carbon dioxide as it drives. It's also emitting other things that are bad for the environment and for human health. So it's emitting particulates, smog precursors, a bunch of things that we would like to get rid of. But we don't necessarily want to stop getting from A to B in our cars, right? So as this vehicle is driving along, it's releasing greenhouse gases. My research asked the question, where does the gasoline come from, and does that matter? So there's lots of different places around the world that are producing gasoline, and lots of different types of oil. So gasoline itself comes from petroleum that we need to get out of the ground, and how we get that petroleum can have an impact on the overall greenhouse gas emissions associated with this car. So we see the emissions coming out of the exhaust, and those are bad. We'd like to get rid of those. But we also have all of these emissions associated with getting the oil out of the ground, processing it, shipping it, dispensing it at the gas station, all of those things that we want to consider so that we get the big picture. It also matters if it were an electric car. So an electric car is nice because there's no greenhouse gas emissions, no emissions from the car itself, right? An electric car driving down the road, it's quiet, there's no greenhouse gases, there's no smog coming out of it, it's clean. But it really matters where that electricity came from. So here now I have an electric car. So it's a green car that you could plug in. Even though we don't have any tailpipe emissions, so nothing coming out of the car itself, we still want to consider where the electricity came from that we use to charge the battery in the car. So just like when we charge our cell phones, right? We plug it into the wall, it looks clean, right? We don't really worry about where the electricity came from. But in fact, that's actually a big important question. So if we got that, if we got that electricity from coal, for example, sorry, this was the best picture I could find for coal mining. So if we were mining coal and we kind of pulverize it, we combust it, and we generate a whole bunch of steam that can turn a turbine, and we get our electricity, and we ship that wherever we need it to go. We've been doing that for a long time, right? But there's a lot of bad emissions associated with the coal that are now also associated with our car because we're using the electricity that was generated from the coal. On the other hand, if we were to produce that electricity with wind turbines, now we have no emissions at the car, no emissions at the wind turbine. So that already sounds better. To take a full systems level approach, we also want to consider how we made those turbines. So if anybody's seen those wind turbines, they're kind of enormous, right? You can see them from a long ways away. They stand quite tall. There's a lot of material that goes into them. If we have to make steel to make the wind turbine, then that requires a lot of energy. And maybe the energy that goes into making the steel that builds those turbines, maybe it came from coal. So the systems level approach takes that big picture perspective. We start at the thing we're actually interested in, which is our electric car, and we go all the way back through the chain to figure out all of the energy and all of the sources of energy that it went into moving that car from A to B. So one of the big important methods that we use in order to do this is called lifecycle assessment. So lifecycle assessment is standardized. So there's a set of guidelines really about how to carry out a lifecycle assessment. And it's a method for evaluating the environmental impacts over the entire life cycle of a product or a process. So in the flow chart here on the right, I have a life cycle for gasoline, for example. So everything within the blue box is something that we would consider in our life cycle assessment. So we would consider how we got the oil out of the ground. And so that's going to depend on if it's conventional oil, is it oil sands oil, is it shale oil, and where in the world did it come from? Because different parts of the world produce oil using different methods. So we want to consider how we got that oil out of the ground. Then we had to transport it to a refinery. So it's maybe pipelined to a refinery. The refinery is going to take that crude oil and it's going to break it down into a bunch of different fractions. So everything from heavy coke, which is kind of like coal itself, all the way up to jet fuel for airplanes. So all along that column, or fraction, what's it, distillation column. So all the way along that spectrum from coal to jet fuel, where our refinery is going to separate out all those fuels from the crude oil. Once we've got our gasoline, which we need to drive our car, we need to ship that gasoline to the gas station so that we can get it. And then we need a little bit of energy to get the gasoline from the pump into our car, and then we can burn it, and that's what lets us drive. So when we do a life cycle assessment, we put all of those life cycle stages into a box, and then we quantify or add up all of the inputs and outputs across that box. So if we're interested in the overall energy use to get us some gasoline, we might add up all the energy that goes into this big blue box, and that's used by all these individual processes. If we're interested in greenhouse gases, then we would count up all of the greenhouse gases emitted by each of these processes, and we'd get one big number of emissions coming out of our overall box. So sometimes you hear this called a cradle-to-grave approach. It's for transportation, it's often called a well-to-wheel approach. So it's counting for all of the impacts from the oil well all the way to where the oil is being combusted to turn the wheels on the vehicle. So well-to-wheel. You might also have heard the term carbon footprint. That's very similar to this. One of the important pieces about life cycle assessment is that all of our emissions or all of our environmental impacts are reported on the basis of a functional unit. The functional unit relates all of our impacts to the function that they're actually serving. So for a vehicle, if you need to get to school, you don't really care that, you don't say, okay, I'm going to go out and I'm going to burn 10 liters of gasoline to get to school. You say, I need to drive 5 kilometers to get to school. Okay, so that function is your kilometers driven. So when we're talking about the greenhouse gas emissions from transportation, our emissions are usually reported in tons of carbon dioxide equivalent per kilometer driven. If you were talking about energy for lighting, that's actually not, it's kind of more of a complicated example. For electricity, so the emissions associated with electricity, it's usually reported per kilowatt hour generated. So that would be the amount of energy, the total CO2 emissions per unit of energy provided to a consumer. Okay, and then I had this sort of popped up early, but this functional unit is also really closely related to the idea that it's the function of our energy that's important, right? We really don't care too much where our energy came from, as long as it's there when we need it, right? And I don't even really care that I have energy. I care that the lights come on and that I can drive, or that I can actually get from A to B, right? How that happens on an everyday basis doesn't really matter as long as it happens, right? So one of the things that's important when we talk about energy systems is we have to keep our mind open to new ways of providing energy services. So it's the energy services that we actually want, or those functions that we want, and then we can explore all different ways to provide those services and functions. So one of the tools that we can use for life cycle assessment is called GGH Genius. This is housed or maintained by Natural Resources Canada. So this is a slightly older version of the model that I happen to have, but it lets you model or do an analysis of transportation fuel emissions. So this is a little bit rough, I guess, but it gives you an idea of what I've been talking about. So this graph is showing greenhouse gas emissions in grams of carbon dioxide equivalent per kilometer driven for gasoline in Ontario, an electric vehicle in Ontario over here, and then an electric vehicle in Quebec, and an electric vehicle in Saskatchewan. So with our gasoline vehicle, the most typical type, most of our emissions come from actually driving the car. Okay, so actually burning the fuel in our car, that's where the most of our emissions come from. But then you can also see this blue part is the fuel production, so actually making the gasoline. This sort of gray color is the oil production, getting the oil out of the ground. And then there's this chunk on top where we actually have to make the vehicle, right? There's a lot of energy and emissions associated with that as well. If we look at our electric vehicles, in all of these cases, we are doing better than if we were burning gasoline, but it varies a lot by province, right? So in Ontario, we have, our electricity grid is a pretty good mix. It's got fairly low greenhouse gas emissions intensity overall. We have a lot of nuclear, which has low life cycle greenhouse gas emissions. We have a lot of hydro. So our blue bar here, now, well, for all of these electric vehicles, we have no emissions from the actual driving of the car, right? So that's our tailpipe emissions. Nothing comes out of the tailpipe of an electric vehicle. Nothing's being burned. But our blue bar, that changes a lot depending on which province we're in. So that's our electricity generation. So in Ontario, we're about here. In Quebec, they have a lot more hydropower, right? So they have an even lower greenhouse gas emission grid than Ontario, and so they have an even lower impact. In Saskatchewan, they still use a fair bit of coal, right? So they have higher emissions than Quebec and Ontario, and so they have a higher emissions associated with the electricity generation. And so for these electric vehicles, it really depends, or their performance relative to gasoline really depends on where you are in the country. And this is a little bit simplified. There's also things to consider about how you drive the car, whether you're in the city or on the highway. But just as sort of a high level perspective this is a good example of the systems approach. So just to say again, why we need a systems level approach is to make sure that we get the complete picture, right? So we have the full picture of our energy system, not just part of it, and not just the part we think we know. A lot of times we think we have the answer, and oh, of course, that's obvious, it's going to do this. But then when we actually do the analysis, sometimes we find that it's not quite as straightforward as we thought it was. So just maybe running a little bit long, so we'll just maybe talk about how we choose an energy source. And it's not easy. So all of our energy sources have pros and cons. None of them are perfect. So my opinion is that we really need a mix of a bunch of different types of energy sources. So we need to consider the environmental impacts. So the emissions, so emissions to air, I guess is what I meant there. So greenhouse gas emissions, those emissions that might cause acid rain or ozone depletion. Something like solar doesn't have those types of emissions on the site, right? If you look at a field of solar panels, there's nothing burning, nothing coming off of them, but they do cover a lot of land. And so that's important as well. So we need to consider the land use. Some energy technologies require a lot of water, and that can be quite important. Varies a lot depending on where you are, but also with climate change, water could become a bigger issue. Social factors are important for energy systems, partly because energy can't be too expensive, right? Everybody needs some amount of energy just to survive. So we have to make sure that everybody can afford some energy. It's also a question of where to put the plants, right? Not many people like to live close to an electricity generating plant, for example. Even wind turbines, I think they look okay, but a lot of people don't like the look of them, right? So they don't want to be able to see them out their kitchen window. And so that's important. We also need to consider the cost. So again, energy can't be too expensive. And all of these different energy systems and energy sources have different costs associated with them, right? So we might be tempted to go with the one that costs the least, right? The cheapest form of energy. But often the cheapest form of energy is the one that has the most, or has a lot of problems associated with it. So for example, coal can be quite cheap if you went and bought a lump of coal, but there's all kinds of environmental impacts associated with it. And so we call those externalities. And so those are things that they're not accounted for in the price. So if I go to buy a lump of coal, I'm paying for the coal. I'm not paying for having to fix the smog emissions or having to fix the acid rain, right? And so if you've heard talk about a carbon tax or a cap and trade system, those are ways to try and build the cost of the impacts on the environment into the cost of our energy so that we get a more fair comparison. We also need to consider technical factors. So not everybody has every type of energy, right? People want to use the type of energy they have. If they don't have to buy it from the country next door, that's something most people would probably be happy with. But not everybody has all of the energy sources they'd like, right? So not everybody has a great solar resource. Not everybody has enough wind. Not everybody has coal in the ground that they can dig out, right? So there's a lot of different factors that we need to consider when we're looking at choosing an energy source. And so I guess my takeaway would be that we have to sort of do these systems level analyses so that we understand all of these different factors, and then we at least have all of the information that we need to make the best decision that we can. So 11:19, maybe I'll stop there and just take questions.
Perfect. Well, thank you so much for sharing all of that with us. If you want to go ahead and click the red stop share button, we'll be able to see your image a little bit larger there.
Okay, yeah.
As we answer questions. Questions we do not have a shortage of at all. So if you saw me while you were talking, Dr. McKellar, that I was feverishly doing a lot of this, looking at two computer screens while I get all these questions sort of taken into another screen, so I'm ready to ask them. So let's get to it. First question is from Ms. McGee's grade 5s in Toronto, Ontario. And Daniel wants to know which is a better source of energy, fossil fuels or nuclear power?
So that's a good question, fossil fuels or nuclear power. So there's a lot of differences between them, right? Both of them are good for, so when we talk about electricity supply, we need sort of a base load power, and then we need some power that can go up and down as we use more and less, right? So nuclear is good because it gives you base load power. So it's just sort of always generating at a constant level, right? And it doesn't emit any, from the nuclear plant itself, it's got a very low life cycle greenhouse gas emissions perspective. No smog pollutants coming from the plant itself, really. But it does have waste, right? Nuclear waste that we need to decide how to handle. And it also tends to be very expensive if you want to build a new, So nuclear can be very expensive to build a new plant. But once it's built, it can be relatively cheap. Coal can be cheap to build, cheap to buy, cheap to operate, and is good for ramping up and down. So if you need, all of a sudden need quite a bit more power, you can turn on a coal plant, but it has all those negative environmental impacts associated with it, right? So the greenhouse gas emissions, the smog emissions, all of those things that we would like to get away from if we can. So they kind of have different roles. My personal opinion would be we'd like to reduce our usage of coal and maybe use more nuclear if we had to.
Okay, and on the heels of that question, we have a question from Phoenix at Edgewood, wondering if nuclear energy produces radiation pollution.
Does nuclear energy produce radiation pollution? Is that the question?
That's the question.
So there's strict regulations around how nuclear plants operate, and they're monitored very closely so that they're always operating within the regulations, right? So they're not allowed to emit radiation, and so they're always careful to operate within that. So no, while they do use sort of radioactive materials, the plant itself, I think my best answer is they're within how much they're allowed to emit. Okay.
Okay. And shifting gears a little bit to another energy source, Tessa would like to know whether turbines in water disturb the animals in the water. So we didn't talk about this in your presentation, but we have wind turbines and we also have water turbines. Maybe you can touch on that.
Right, and so it could. So if you have, for hydropower, we have some big hydro systems like Niagara Falls, right, big waterfalls. But there's also some smaller, what we call a run of river. So you just have a fast-moving river, and you could put a turbine in it to capture the the energy from the water. And so theoretically, yes, if you had fish that had to go up that river, they could be hurt by the turbine. There are things you can do. You could make a separate path for the fish around the turbine. So they rather than having to go through the turbine, they can bypass it, right? And so before any type of energy system like that is built, the person who wants to build it has to go through an environmental assessment and consider whether it's going to hurt the fish. And then before the government lets them build it, they would have to decide whether they were happy with that or if they could fix it or what the problem there would be.
And it's interesting that you just mentioned electricity, energy, because we have a couple questions coming from Mr. Baxter's class in Toronto. Both Carson and Isaac are wondering about what exactly energy is, and they've learned that it can't be created or destroyed. So does that mean we have an infinite supply in the universe? And how does this relate to our use of energy or when we talk about electricity?
Right. So yeah, energy can't be created or destroyed. I'm not sure there's an infinite amount. Possibly. I guess if the universe is infinite, maybe there is an infinite amount. When we're talking about how we use energy, it's always about energy conversion. So if we have oil, the oil has a bunch of chemical energy stored in it. When we combust it, we release that chemical energy as heat. We take that heat energy and use it to heat water. The water turns into steam, and then the steam turns the turbine as mechanical energy. The mechanical energy in the turbine powers the generator, and that's how we get the electricity. So we're always converting energy from one form to another. And every time we do that, we lose a little bit. So that's what we talk about with efficiency. Something that has a low efficiency loses a lot of energy in the conversion. High efficiency would do better.
Right. And now we have a question from Ms. Holloway's class. Sujal wants to know, why aren't there any plans to build electric rockets?
Electric rockets?
Are we getting a little bit outside of your
expertise? It's a little bit outside, but I think, so yeah, I'm not an expert in rockets, but you need sort of, for a rocket to take off, you need a big burst of energy, right? So you kind of, I'm picturing like a cartoon flame coming out of the bottom of the rocket. With electricity, you'd need something to create that thrust, right? So you'd have to accelerate, I don't know, accelerate air, I guess, or some water, something to push the rocket up. And so I think you would just, that's an excellent question. I'm not sure how you would accomplish that with electricity.
I think we might have to take that question to one of our astrophysicists maybe to talk about the energy.
Maybe.
We have a question now from St. Cattery. One of the students there is wondering, how much oil is refined to make 1 liter of gasoline?
Oh, that is a very good question. I don't have the number off the top of my head.
Can you give us a ballpark maybe, or an idea? Is it similar? Is it, a liter of oil, or is it 10 times as much?
No, all those, it's been a while since I looked at those numbers, and they've sort of lost me. So if you kind of picture a barrel of oil, a barrel of oil can be broken down into sort of the heavy stuff, so coke and asphaltenes. It's going to get some fuel oil out of it that maybe would go in a furnace. Some diesel fuel, gasoline, and jet fuel can all come out of a single barrel of oil. Sorry, I don't remember the numbers there.
No, that's fine. It's just proof that even our experts don't know the answers to all the questions.
I still have to look things up, yeah.
Yeah, and so now if you really want to know the answer to that question, I suggest you do a little bit of research yourself.
There you go.
Let's switch gears and talk about solar a little bit. We have a question from Ms. Perry's class at Frederick Banting in Ottawa. We have a question there. Solar panels can be on the roof of homes or buildings. Therefore, land use would not be an issue. Will the Government of Ontario continue to promote solar? And do you think solar is a good option in Ontario?
Right. So yeah, if you can put solar on the tops of houses or on the tops of big warehouses, or in Oshawa here, we have solar panels on the roof of the big arena downtown. So if you can do that, that's a great alternative to covering up good land, right? Land that might better be used for farming, for example. So the Government of Ontario was promoting solar through what was called the FIT program, the Feed-in Tariff program. And so if you signed up for that, you could install a solar panel on your roof or on the ground and sell the electricity to the government, and they would guarantee that they would pay you a high price for a certain number of years. And so that worked, well, depending on who you ask, it worked well or not so well. But it did increase the amount of solar that we have in Ontario. And there were rules. I think they did prefer to have the solar panels not on the ground covering up the land. So I think they did prefer to have them on rooftops or on buildings. I do think solar can work in Ontario. I'm not sure we could switch to 100% solar, but I do think there is a role for it to play. So I think we need a little bit of everything. So we could have some PV panels. When we have good sun, we could make a lot of power. You can also get hot water from solar panels. So you can put a different type of solar panel on your roof and use that as part of your water heater rather than having to use electricity or natural gas for hot water in your house. So yeah, I do think there's a role for it to play.
Excellent. And now we have a question from the grade 6s at North Agincourt in Ms. McClinton's class, wondering how dangerous are nuclear power plants?
So nuclear power plants, I would say, are not more dangerous than other types of plants. Just like every type of energy has good environmental impacts and bad environmental impacts, different types of energy also have different safety concerns, right? And some of them we're just more familiar with. So, I mean, a natural gas plant, natural gas can explode, right? A nuclear power plant, there are risks associated with it, but there's so much regulation, so many rules that they have to follow to keep those operating safely that I wouldn't say it's any more dangerous than any other type. Well, once all the regulations are there and everyone's following all the rules, they're not really any more dangerous than any other type of plant.
And we have a question from Ms. Wolfson's class, wondering how does nuclear waste fit into the system level approach? When you're really talking about beginning to end, we're getting the energy in the middle, but we know there's some waste. How does that fit in when you weigh up whether or not we should be using nuclear, or what proportion of nuclear to use as our energy source?
Right, and so I have a student actually who's looking at this type of question. And so we do, if we're taking a systems level approach, we do want to consider the waste that's left at the end of a nuclear life cycle, and we do want to consider how we have to handle it. That's all part of the big picture. When it's a little bit more important, the nuclear waste, than waste from other types of facilities, just because it has to be managed more, it has to be stored carefully. But on the sort of grand scheme of things, when you look at, so when I mentioned the life cycle assessment, right, everything was reported in terms of a functional unit. So for electricity generation, everything is reported in terms of the kilowatt hours that a plant produces. So when we look at the nuclear waste piece as a function of all of the electricity that plant generated over its 50-year lifespan, the overall contribution of the waste management isn't enormous, right? It's a little bit more important than it would be in some other plants because there's more work and because there's fewer emissions from the plant itself to sort of balance it out. But it's not a huge problem from that perspective.
And although I do see there are quite a few questions we haven't had a chance to ask yet, I think we've covered the flavor of most of these questions, with the exception of one of my final two questions, which has been asked several times by classes. In your opinion, what do you think is the best energy source? Or is that maybe too simplified of a question?
I would say there isn't sort of one best. I think we do need a mix. They all have advantages and disadvantages, and I think our best bet is to use a mix. If we could get rid of fossil fuels, ideally, I mean, that would be good because we would get rid of all the climate change emissions. We just need to make sure that we can replace them with something that's going to do the same thing in terms of being able to turn on and off. So my ideal, if I could find something that was base load power and peaking and no emissions of greenhouse gases or smog precursors, didn't take up too much land, didn't disturb the wildlife, and everybody liked it, that would be fantastic. But until then, I think we need a mix of things.
That makes a lot of sense. Last question for you before we sign off today is maybe a little bit about how you got to where you are, or advice for students who might be really interested in pursuing a career in this area.
Right. So my undergraduate and master's degrees, so my bachelor's and my master's, are in chemical engineering. And I did, in my undergraduate, I did an environmental engineering sort of focus. And then I worked a little bit in consulting, and then I went back and did a PhD in civil engineering, but still on the environmental engineering side. So if you're interested in energy, Engineering is a great way to go, but you can also get there through science. I know at UOIT here, there's a lot of people in the science faculty, especially physics, who are looking at different types of solar and fuel cells. We're working on a Bachelor of Technology program in energy systems, sustainable energy systems here in my faculty. But I think energy is so broad that there's lots of different ways to go about it. So even if you wanted to come at it from the social science perspective, someone who not as interested in the math and science, but still wants to help with energy, I think there's a lot of opportunities there as well for figuring out what people like and how people use energy. So it's a broad field.
I imagine there must be lots of opportunities, not only for that scientific engineering research, but also policy making and things like that.
Yes, yeah, trying to help. So all the questions that, the students are asking, these are great questions. And these are questions that the politicians need to come up with answers to. And sometimes, the answers are kind of vague, right? But they still need to do something. And so someone who can help them make those decisions, that's very helpful to them.
Wonderful. Well, that is all the time we have. We've actually gone over time today because we had so many great questions and lots of good discussion happening. And I do see in the chat we've got several classes already saying their own thank yous. Thank you from us at Partners in Research Canada as well, Dr. McKellar, for your time today.
My pleasure.
So next week, we are discussing First Nations water quality on live event. More information about this webinar and other PIR educational programming is available at pirweb.org. Thanks so much for tuning in today, everyone. Have a good one.